Okay, welcome back. This is the third seminar in the set of seminars for mobile embedded devices, and this week we're going to be looking at make and makefiles. Now, the previous week we looked a little at compilers and some of the associated tools. Make is really the other majorly important tool which you really will need to know about and understand. It's no great exaggeration to really say that make is the sort of glue that holds the internet and a lot of modern computing together. And so if you don't really understand make, then you don't really understand quite a lot of modern computing and the internet. So you've really got to get to grips with it. Okay, so in order to understand make, first we need to get some terminology correct. Now, next year you'll be going into industry and working and being paid as a computing professional, and terminology is important. So it drives me and many of my colleagues crazy when students says the thing doesn't work or it didn't work, and terms like that. You've got to try to become more precise in your use of language and your descriptions of problems, because basically the woolly language you use betrays woolly thinking. So make, what do we understand by make? Well, when you download the worksheets and you have a look in the worksheet directory, you'll notice there is a makefile. Now, make and makefiles are related, believe it or not. Make is the command, and makefile is the set of commands which make will operate. If we type in man make to get, man make, not man make, oh good, man make. If we type in man make, we'll see that it says it's a utility to maintain a group of programs. That's not really. GNU is the development behind a lot of this, or the developing organisation. Now, down here, it's a little better description. It says, make is a utility which will determine automatically which pieces of a large program need to be recompiled and issue the commands to recompile them. Now, although that's true, it's only partially true because it's not necessarily programs. It can also be documents, it can be help files, it can be all sorts of things. It is mainly programs, but it isn't just programs, and you'd be misled to think that that was the only truth of the matter. Now, as with most commands, it's got a number of flags. Not as many as GCC, thank God, but there are a number of commands. Now, if you type in make on its own, it looks for a makefile and decides what needs doing. And here it just says there's nothing needs doing. Okay, so make reads the makefile. And it is possible to point it at other makefiles. So sometimes you might have makefile.linux.windows 10, whatever. Okay, so it is possible. Now, just before we go and look in detail at the makefile, which is reasonably complicated, let's have a little look to see other examples of makefiles. So, for example here, I've typed in Linux source code browser on Google. Now, Linux obviously is the operating system I'm using and you'll be using for this development. It's a very large program. It's central to the running of operating systems. It's central to the running of Android, for example. Routers and televisions and all sorts of things will be running Linux. So big program, very important. And if we go and use a source code browser, so a bit slow at the moment, but it's virtual machines for you. If we have a little look, and this is the source code browser for the Linux kernel. And here we can see there's all sorts of, there's some documentation which is generally pretty out of date. There's the kernel, various device drivers, some very dodgy dates there. Any date that says the 1st of January 1970 is a mistake. Basically, that's the beginning of time as far as Unix is concerned. So they obviously haven't set their clock correctly. And down here we see a makefile. Now, the makefile itself is a Linux one, and so consequently you get all sorts of weird stuff in there, because basically only developers look at this stuff. Normal users will never, ever, ever see this. So they feel fairly relaxed. And you'll quite often find it has quite a lot of honest commenting in it. Now, the makefile itself is big, okay? There are some bits that later on you will start to notice similarities. So somewhere down here there is some stuff on cross-compilation and on architecture. So there we are, it's using, if it's doing cross-compilation, if it's using architecture. And lots of these commands are built-in make commands or Linux shell commands. Now, this makefile itself is, and the Linux makefiles are so complicated, you generally don't edit them by hand. You use other programs in order to edit them because they're too complicated for us to edit. So that's just the top level. If we go into the drivers directory and maybe go and look, so lots and lots of device drivers for you know, things like hard drives and graphics, memory chips, and network, for example. And here we've got network, and there's another makefile. Okay, and this is a simpler makefile because it may or may not be including, you won't have all of these devices on your machine, so only some of them. So if you had Ethernet, you'd then, there'd be a different chip. So if you're using, I don't know, the Broadcom chips, then there's a makefile. Okay, so the whole thing is held together by makefiles. Now this isn't just Linux. Mozilla Firefox has makefiles. This one you'll see is called makefile.in because it's used by part of the automatic build process, the same as the Linux one. You don't generally edit them. There's some small areas that you would edit manually. Okay, so there is no real exaggeration in saying that these things sort of hold the internet together. And without them, it'd be impossible really to build complex programs and systems. Obviously on top of that you've got things like Git and source code control systems, but they're really beyond our remit in this set of lectures. Okay, so now let's have a little look. We've already seen that if I type in make, it says demo.elf is up to date. If we now look at the makefile itself, the makefile has some comments, and this being the comments are not great, but there are some comments at least. And then a whole series of directives to make. Now, the very first one is normally very important, and this is normally known as the target. Okay. Now, the target here is something called elf, and it's set to a program called demo.elf. So that's what it wants to do. And down here, it has a whole set of rules which tells it how to achieve this. Now, in our instance, so it just says here, build the executive, build demo.elf, and this is how you do it. And what it says is it looks in the directory and says, well, you've already got one. so I don't need to do anything. Now if I remove demo.elf, it will actually then do something. It makes demo.elf. It goes and does one of the particular rules down here. Okay, so we've got a target and we've got some rules. So with the target here, demo.elf. Now if I needed to change that target, I could change that here. And the whole idea of this is to make it very open and flexible. So it isn't just limited to making one particular file. Now, I'll skip a moment over some of these settings here because I want to go into those in detail. But this tells it what its target is, okay? And this gives it a whole set of rules in which to try and execute that target. And it actually says, okay, I want to do this, I need these things. And if I've got those things, I will do this action here, okay? Now, because it had demo.elf originally, it looked at that and said, well, I don't need to do any of that, I'm done, okay? Now, there are other labels here, so for instance, clean and debug. Now, they are just standalone labels. And I can call those directories, so I can say make clean. And what it does is it says do this whenever I say that. And it says remove $obj.d and $elf. And the obj are the .o files, object files, the .d files are dependency files, and demo.elf. Okay. And if we do ls now, those files have gone. Okay. Now, how did it know what these were? Well, it looks up and says, oh, these files called obj are here, they're listed here. And anything with a dollar in front of it is a variable and needs declaring. So startup is in fact startup stm blah 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 and system stm blah 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 .o. So they're all .o files. Okay. So it then knows that that's the name it's going to pick. And here it modifies the .o files into .d files. To be quite honest, you don't really need to know that much about dependency information at the moment. That's really for larger systems. Okay, so once we've done that, and we can rerun the command as many times as we want. And the reason it has -f there is that says force, which means don't complain if it's a dumb thing to do. Now, if I actually issued that command, and I can issue it directly, okay. So let's just issue the command without the -f and see what happens. And RM just says, oh, can't do that. Okay, so to stop it doing that, it has -f. Okay, it's basically shut up. Now, what happens when I run the system? So if I ran it before and demo.elf was there and it said nothing to do, and when I ran it the second time, demo.elf wasn't there, but obj were. And as we remember, obj are this set of files here, object files. Okay. So what happens if they're not there? Well, the system goes and says, okay, I need to, in the previous one it said, I need to do demo.elf, I need .obj, oh, they're there, and I'll do this. Okay, so it runs this command, and I'll explain that in a moment. Now, if $obj aren't there, if all of these files don't exist, and if we look in the directory, they've gone, because we did make clean, then the system needs to do something. And what it then does is it looks through its rules to say, can I build those object files? Do I have a rule that will allow me to achieve this target? And so it steps through and it says, hey, if your target is something, percent just means something, it replace with a name. So the first one I'll go through is startup STM32F10X.O. It says, if you want a .0 and you've got a .c, then do these things, okay? And you'll get one. So it does that. And then it goes to the next one, which will be system, blah, blah, blah. And it says, hey, if you've got one of those, do that. And then it goes, so it can just step through each of those. And all of this sort of weird hieroglyphics is really just allowing the system to run these rules in a generic format. Okay, and we'll see in a moment how that operates. Now, it actually hits the rules in order. Okay, so it will just try that one, then try this one, then try these, won't match, so it won't do them. Unfortunately, it hits this one and finds it. Okay, if it needed a .o file and it didn't have a .c file, but it did have an assembler file, then it would run this particular command. We're not building, I don't think we're building assembler files, are we? No, we're not. So that really is untried in the system. Okay, so, and if we look through now, if I say make, what we'll find is it runs through all of these. It builds these dependency files as well, but it runs through system.o, rcc.o, gpi.o, main.o, and then it gets to the bit that it got to before, where it says, hey, I can now build the binary. Now, the next thing we need to understand is what's all this about, okay? And this, again, is supplied via the makefile. If we look at the makefile, so we've got our target, we've got our set of rules, and we've got our variable telling us what the objects are, and these bits will be edited later on as you go along, because obviously as we start using other devices, other aspects of the hardware, so the USB or the Ethernet chip or silicon, then those will need pulling in. So these will need changing. There are a whole set of other variables. So here is a variable called tool root, and this is saying where the compiler is. Now, this is assuming that the variable path isn't set correctly, which generally is a sensible thing for a makefile to do, because it doesn't really know, particularly if it's doing cross-compilation, because they could be strange. However, that path name, if you use this on the machine at the university, it won't work, okay? Because root code source root, blah, 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 won't exist. And this is a common thing to need to change, okay? So that may well need editing. And if it then gets to these rules here and says, can't do that, then that's the likely problem. And the simple thing to do is just check to see if that path really exists. And it might exist, but you don't have permission, for example. Next, it's saying where the library code is. Now, for the device, ST Micro have provided us with a fairly extensive set of library routines written in C, which we've got the source code for and we can use. And we're using two of those. We're using the clock setting, okay, so the clock controllers and the general purpose I/O controllers, because that's what our program does, okay. Now, those bits of code are not going to be in a standard place, okay? If I were building this natively, then I wouldn't need to do this. I wouldn't need to say where the compiler is. I wouldn't need to say where the libraries are. because on the normal system, the native system, we would use GCC, okay, the standard compiler, and there are standard places for the library code. And because this is a virtualized machine, it's not terribly interesting. But there's various libraries knocking around, okay, with bits of stuff to do with various parts of the system. So stuff to initialize, stuff for the compiler, the CPU, so on and so forth. Okay, but we can't use that because this is all Pentium assembler. So it's of absolutely no use. So that's why we have to tell the system where to find its libraries. And here they are. And again, that path name could be wrong. Okay, and it's quite common for you to unpack stuff. So if it's in a tar file, if you unpacked it and you've put it in different places, for these things to go wrong. And again, what you will get is you'll get errors saying can't find that file. And basically, you either have to modify the makefile in order to look like the reality of the file system, or modify the file system to look like the makefile. It's sort of up to you, really. Okay, so we've told it where its tool chain is and where its library code is, because we're doing cross-development. And now we're setting up the specific tools. So this is the C compiler, and we're giving it the specific name there. Now, again, because the path variable set, I can actually do that without any of this. But in general, it's a good idea to not make assumptions. And we've got a linker, we've got an archiver, I don't think that's used at the moment, and an assembler. Okay, so they're the tools we're using. And later on, you might find there are more tools that get used. Now, the library itself is the top level library. And as you noticed, if you looked in the library stuff, there are various bits of the library knocking around. So that's the Pentium library. So that's got the various bits of stuff for running the Pentium. There's stuff to do with modules and to do with terminals and various other things on the system. Okay. Now, these are the sets of code paths that we need for the various libraries. Now, Synthesis is the name that ARM have given to their BIOS, basically. So that is the BIOS that runs the machine. So as when you boot a PC, it's got a BIOS which starts things up. This is the BIOS here. And CM3 is the Cortex M3, which is our system. Okay, so, and these are the library routines for our specific device. There are lots of different Cortex F series, and there's F1s and F4s and all sorts of different devices. And this is the core support. And then finally, there's the peripheral libraries. So the ones which have this bits of code in. So if we look, so it says that the library is in STM, where is it? Oh, I've got a space there. STM32F, there it is. And then libraries, so CM3, Synthesis, CM3, and there's core support and device support. So if we look in core support, and that's the two files, the two C and header files, which need to be built in order to build the core of the firmware or the BIOS for our piece of hardware. If we look in libraries, stm32f and look in source, and then we'll find there's rcc.c and GPIO should be there somewhere. There it is, GPIO.c. Now these are the devices like I2C and flash memory and DMA and digital to analog, analog to digital converters. So there's lots of different bits and bobs there that we will later on see. Okay, so we've told the system where to expect stuff. And like I say, these things can change and you get a new device or a new version of the library and stuff will move, okay? So this is the sorts of bits of the file which you will normally file. And it's really, really common to pick up makefiles rather than write them all from scratch yourself. Okay. Now, in order to speed things up, it's got these path variables which allows it to search quickly through those in order to find the files it needs to speed things up. Now, if we were doing something like the Linux system where you've got thousands of files and it could take a long time to search things, that's worth doing. Ours, probably not really. But anyhow, we're searching through looking for all of the C files in the various places. And there it's actually saying it's in peripheral source, okay? So, and later on we'll see peripherals include, because those are separated out. So this allows the system to go off and find all the files it needs, so that it can find all the header files, it can find all of the .c files. Now we're getting a set of other variables, and this one is telling it the model, and our model of the M3 is called connectivity line device, which means that it's got lots of networking. It's got Ethernet, it's got I2C, it's got lots of UARTs, so on and so forth. So it's that particular device, and we need to tell, particularly the libraries, this piece of information. We'll look later on at this script here, but this is called the linker script, the link loader script, and we'll actually do a completely separate seminar looking at linkers and linker development scripts. We've already seen startup, it's just some extra files to add to the list there. Startup and the other objects could all be put in one big long list, but it does seem sensible. Those two are somewhat different. They're in here, yeah, they're all in that directory, I'm pretty sure. Actually, one of them might be local. Okay, we've now got some compilation flags, -O, 0, and -G. Now, if we wanted to find out what these flags actually mean, we would need to look in command gcc, and then search for -G, for example, and we'd find it all over the place. Okay, so it could take a long time, so I'm not going to do that. But you can find those flags out. The -O flag is for optimization, and we're doing optimization of no optimization, basically. We're not optimizing at all because we basically want to do everything ourselves as much as we can. Now, optimization is very, very good on compilers. It's really impressive. But on embedded systems, you need to be a little careful with it. So generally, you tend to have it at fairly low levels. G is global symbol table, meaning that we can debug the code, which will be useful when we use the GDB debugger. For release, you would get rid of that, okay? So, one of the big hacks in the 1990s, I think it was, of the internet was because somebody forgot to delete that flag from a makefile for mail process, and everybody could figure out how to hack the mail process. So be careful with those things. Okay, we've now got some more compilation flags, so that's this for GDB, optimization, and global symbols. These ones here So minus D are nearly always their defines, which means they're for preprocessors. So they're basically telling the preprocessor what to include, and you'll see there's some other ones here, minus D type, use standard peripheral library, and $full assert. Okay, so all of these flags are really to do with the preprocessor. So they're including the correct header files, local header files, ones from device, core, and peripherals. And interestingly, you'll notice that it does dot and then dot at the end, because basically it wants to make sure it double checks, because there may be a header file which is referred to in one of these which is local, and it may not have picked it up on the first run through. So that is quite often done in order to make sure that, because it tends to do this, well, it does do these things on single passes. These flags here, this is the linker script, and like I say, we'll look at that later on. These things here are standard compilation flags and loader flags. So the compilation flags, anything with minus M is to do with the machine, okay? And CPU is very clear, it's Cortex-M3, and it's using the 16-bit instruction set called thumb, rather than the full ARM instruction set. Rather confusingly, they say arm and thumb rather than finger and thumb. But there you go. These ones here are used by the linker, and it's saying don't use the standard library. Now the reason it says don't use the standard library is because we're providing all of the library code. Now normally a compiler would expect to use a very standard library. It's also saying build statically, include all of the code, don't use dynamic libraries, and then a reiteration of those instructions there. So when we get down to here, we can start to understand this a little bit more. Okay, so it says use the C compiler. Fine. Minus C means stop a compilation, create object files, and then use the C flags. So the C flags are all of these things here. This is now saying use as input whatever name is given here. So on the first run through, it will be startup stm32f10x.c, and it will use that there, and then it says put the object file into, and this variable here refers to this. So it then puts it in there. I'll ignore the dependency files for the moment. Okay. So it allows it to run through and iterate through each file. So if I do make clean again, and then do make, we can see that it's done those commands. So we've got the minus C, minus optimization level, global symbol table, the machine dependencies there for the Cortex, thumb, and then the various header files, and then the input file, which is startup, so blah 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 .c, and that's the output file. Now obviously if those files are incorrect, make would stop. So if there was an error, if the C compiler said, you know, if there was some nonsense in one of those files, then it would just stop and say can't carry on. Okay. If there's a warning, you'll just see the warning, and make will ignore those and carry on. So as long as all of this works, then it gets to this line here, which is this line here, and it's using the linker, as we've seen up the top. It's using the linker description flags. It's outputting into demo.elf. It's got the object files which were created down here, and $libs, LD-libs. And LD-libs isn't actually declared at the moment. We use it later on, but it's not actually needed at the moment. So that will just come out as a null variable, and it won't complain about that. If a variable's not been declared, it just says fine, whatever, and just carries on. Okay, so now we can look in our directory and we can see what files we've got. So, oops, file start.o, and there we are. We've got ELF32-bit ARM relocatable object files, okay, and it's not stripped because it's got a global symbol table. If we now say file demo.elf, and this is executable, it's statically linked, not stripped because it's still got the global symbol table. If we remove the -g option, then that would get rid of that for us. Now, that's given us the opportunity to build a binary file, and we'll look in the next session at what is actually in that binary file, how is it executed, and in particular we'll look at the linker description file and the startup files. Okay, thanks a lot.